Hello everyone, welcome back to Dragonfly Engineering. This week is the second episode in the Stoker Steam Engine restoration project, specifically to remake the piston rods, and in the last episode we remade some castle nuts that connects the piston to the piston rod. And this is all in collaboration with Keith Rucker of VintageMachinery.org, who in turn is collaborating with Nashville Steam Preservation Society. And the Stoker Steam Engine, which shovels coal into the back of this locomotive, will be part of this locomotive. So the Nashville Steam Preservation Society is restoring locomotive number 576. This piston rod has a tapered tip. Oh, and Keith had to cut this up to get it out of the Stoker engine, which I mentioned last week. So we've got a tapered end on each side of the rod itself. These tapers we're going to CNC machine. The diameter of the rod needs to be 1.5 inches, and Keith requested that the surface finish on the rod is very smooth and polished, because this rod is actually pistoning in and out of a steam axial seal. So one side of the steam engine, there's high pressure steam exiting the piston, and this rod actually is the seal bushing for the piston. The other requirement is that the rod needs to be concentric. So we don't want any run out from one end of the rod to the other, because as the rod is going through this pressure seal, if the diameter is getting smaller and then bigger, then we're actually going to be working the seal open and potentially causing premature steam leaks into the housing of the engine. So all that being said, we got some 4340 steel that I got from McMaster Car, and it unfortunately is hot rolled, but you know, we got to work with what we can get. So why don't we go over to the lathe, or actually the cutoff saw, and cut off a piece, and then go to the lathe and start turning down this precision dimension. This 4340 rod is hot rolled steel, and it's got a real nasty oxide finish on it. So let's go ahead and load it into the saw here and hack off 20.5 inches. Let's see how well this stuff cuts. The yield strength of this steel in its current annealed state, I believe, is 122,000 psi, so it's pretty tough stuff. Okay, now we can load this hot rolled 4330 into the CNC lathe. This lathe is a TRL 1630SX, and it's probably 8 years old. It's a transitional lathe, or a transitional CNC lathe, so it's not a full production system. There's no tool changer on it, but it's a beginner CNC lathe with kind of tool room applications, so one tool at a time. You can program multiple tools, and you can do a lot of your programming on the floor of the tool room instead of on some computer somewhere. So it's a nice lathe for my needs. I was also considering using the follow rest for this application, because you see we got a lot of stick out on this bar. We will use a live center on the tailstock. That being said, I'm going to go ahead and chuck this bar deep into the lathe so that we can see how we are on a center, and then drill our center hole, and then go ahead and set up to do a facing on this entire bar. So let's go ahead and start facing off this 4340 rod. Gonna add a little coolant. I think in the machinability chart for this steel, it's like 50% of free machining steel, so it's kind of rough to work with, but we'll see how we go here. I'm gonna go ahead and do the first pass. Okay, down to the 0. Let's see what that looks like. You can get a measurement on the diameter, a rough estimate on the diameter. And this steel has the hot rolled oxide coating, which isn't so great for your tools. hence I'm probably going to throw away this older bit once we knock off all this rough outer oxide. The main point here is to drill the center, so let's go ahead and just do that. I think this size will be appropriate. Okay, let's go ahead and drill our center. Sometimes these get hot too. This is a high-speed steel center. Of course, I'm just about done by the time the coolant gets to it. And here we're setting a cone into the center of our part, even though it may not be exactly concentric to this rough outside diameter. This cone that we're drilling into the back of this part is going to wind up being the true center once we turn down the shaft. Okay, so let me back this guy out. Okay, we're going to support the extended length of our stock that we just put the center drill in with this live center. So the center hole that we just drilled in our stock will fit inside of this cone here. Let me get you in focus. And there's a really good bearing which allows the stock to spin in this cone, and it holds the stock cantilevered out from the chuck concentric with the center of what you're turning. In the back of the live center is a Morris taper, a locking taper, and you basically lock this live center into the back of your tailstock. I like this particular live center because the cone is small in diameter, so you can get cutting tools in here from the side. Now if you've got a pipe or something with a large inside diameter, then these larger cones are good because you can just basically seat the center of your pipe on the large cone. And funny story, I actually bought this live center from Andrew Alexander from Blacksmithing Tools at the Good of the Lands Festival. And I'm pretty new to the whole YouTube universe, and so I had no idea who Andrew was. He certainly didn't know who I was, but he had his flatbed out there at the festival selling basically used machining equipment such as live centers and things. So I haggled with him and bought this live center for 10 bucks. And then later on I see that he's the keynote speaker for the entire event. Described how he was selling his tools for very cheap so that they would get back out into the machining world and actually do some work for people like me. So here you go, Andrew. I'm making Keith Rucker's Stoker Steam Engine piston rods with your $10 live center that you sold me at the Good of the Land Festival. So thank you very much. Okay, we're going to set our live center into the tailstock. This is a Morris taper, which is a locking taper, and then the corresponding Morris taper in here. So when you basically push these two tapers together, the shaft locks in place, or the two angles lock. It's called a locking taper. And then you can spin your live center freely, and this thing shouldn't fall out easily. If it does come out, that means you probably got a thin layer of oil in your locking taper and it didn't really seat and wedge in correctly. So if that happens, you just got to wipe off the inside of your spindle and your locking taper face so that you get a good seat. You can also lock down the spindle with this clamp at the top or release it. To pull the live center out when you're done, you have to, for this particular tailstock, you've got to back the spindle up, and inside there's a bar that will eject the locking taper out of its seat, kind of like that. So now I can pull it back out. So that's how you set up your live center. You go ahead and set it back in there. Here we go. Well, this is a 3-jawed scroll chuck. So by turning these 3 keys, some people say that you're supposed to turn all 3 keys equally for best centering. The live center is spinning right now. That's because there's not a lot of tension holding the cone of the live center into the center drilled pocket of the stock. So I'll add some tension so this is tighter and more accurate. The operation is going to be that we're going to cut the cone and the taper on the piston rod on the far end over by the tailstock, and then in the same setup to maintain concentricity, we're going to go ahead and turn this taper on the backside. This is a 3/4 inch per 12 inch taper, and I just need to make sure I have enough room to get the tool in here, so I don't want the tool to jam up on the chuck to start turning this taper this way. I'm going to add some coolant because this almost certainly needs coolant. Hopefully it doesn't spray me too much. I like to just dribble a little bit of coolant. And another thing I do is I kind of splash the coolant on the surface of the carbide tool. It seems to help keep the spray down. All right, so I'm going to manually move the X and Y of this CNC lathe. There's some hand wheels that are tied to servo motors, so I'm not actually physically controlling the lathe axes, but I'm giving instructions to servo motors to move. So that sounds like a reasonably good cut. My understanding is if you try to take too thin of a cut, then you rub instead of cut, and you can get worse surface finish that way. So I am going to set up a power feed. So we're going to tell it to power feed in the Z-axis, let's say 2 inches per minute. And then I will tell it to go. The other thing to consider is chip formation. Or the other thing to be aware of is the size of your chip that's coming off. Let's see if I can catch one. You don't want the chip to feed back into the cut. If it does, then you can mar your finish, because essentially all of a sudden the cutter is seeing extra material than the rest of the cut. So these chips are pretty good. I don't know, let's see if the camera can, let me zoom in on that. All right, so this is what the first pass finish looks like. It looks like there's some micro galling on the surface, which isn't too surprising because that carbide insert was an old one that I was planning on tossing after this first or second pass to get all that oxide off of there. I stopped fiddling with the digital calipers and I got the 1 to 2 inch Mitutoyo micrometer out. I was noticing that the bar was cooling off, so I was kind of chasing my tail with measuring a cooling off bar as well as fussing with the pressures on the jaws. So these are, when you're getting more accurate, micrometers are a better way to go for measuring. So let's go ahead and measure this end. And then there's a tensioner knob at the top that you spin. And then let's see what we got. We got, so there's 1 inch by default, so this is a 1 to 2 inch micrometer. So 1.7016 inches is this diameter. So we're a little over 1/1000th larger in diameter in the middle here. The surface is galled up though, but let's go ahead and measure the other end. And here we've got 1.710, so we're about 1/1000th fat in the middle here. So I don't know if that justifies using the follow rest, because the follow rest can cause all sorts of problems. Okay, I'll show you a little bit of the CNC screen here so that you can see the other half of this turning operation. So this is the ProtoTrack SLX controller, CNC controller for a pretty basic CNC mill. And what we're going to do is power feed, and that's what we've been doing the last few times here. So I'm going to go into the power feed mode, which is here. And then I'm going to tell it, and right now we're set up at a fixed RPM, and the RPM is 500. Feed rate currently is set at 10 inches per minute, but we're going to lower that, so we hit the F on the overrides, and then I'm going to drop the feed rate down to, let's do 2 inches per minute. And then what we want to do is tell we're going to hit the Z axis, which is the direction of travel, and it's prompting me go to Z equals, and then we're going to tell it minus 20 inches point, and then incremental set. And I'll wait until the coolant starts flowing, which it is now. Okay, so let's hit go. Oh, actually I forgot to set the depth of cut. And then we'll do a 40/1000th cut. So we'll do 1.555. Here we go. There's a coarse and a fine setting. So this is fine, which adds an extra dimension or another digit. Okay, so we'll go to power feed. Yeah, so go. Okay, and then that is the cut that we just started with the power feed of minus 20 inches. At 2 inches per minute and 500 RPM. So I bumped around the tailstock a little bit, trying to get that 0.5 alignment knocked in to alignment with the chuck. So we'll see if our cylinder that we're turning here is going to wind up having the same dimensions in the front, middle, and end. So the front diameter at the chuck equals the mid-span diameter or mid-shaft diameter, and then I'm 1/1000 smaller in diameter at the tailstock. So to fix this problem, I've adjusted the set screw and the corresponding set screw on the back side of the tailstock, which is essentially a cross slide. And I put just a little bit of pressure. I loosened this one slightly and added a little pressure in the back to push the tailstock over by hopefully 1/2 thousandths, so that I can get effectively equal diameters on the front, center, and back of this rod. Actually, since I got you here, we might as well check with the DRO if we can see if the tailstock has moved over 1/2 thousand. So the last dimension was 1.5555, I believe. I'm going to come up and just kiss the side of our stock. So that's 1.5545. Well, I wonder if we went 1 or 1/2 thousandths too far on the tailstock. So I don't know. If it could just be a matter of me leaning against the tailstock as we do our next cut. All right, let's hope that did it. So we'll turn off the spindle. So let's measure to see if we are squared up. I'm going to use the calipers because it takes a little less time. We are 5/10,000ths out on diameter on this side, which means that we are 2 to 3/10,000ths out of alignment on the chuck. And I don't think I'm going to be able to make that any better. So I would say we are good. I am then going to do some diamond lapping and polishing. All right, I've zoomed in on the surface finish of our rough cut. This is before I flip the carbide insert around. You can see a little bit of some grooves and things in here. Let me hit it with the Scotch-Brite and see if that helps out with the surface. Sometimes the Scotch-Brite hides defects, so you can see how we're polishing up this barrel. And, this is the maroon Scotch-Brite. I don't know what coarse or grit it is, but this is showing some of the effects from that dull tool. And you can kind of cheat and make things look nice, but there's still some subtle grooves and things on the surface of your shaft that you turn. So there we got a nice, what looks to be more of a polished finish. You can see kind of a defect ring right there. A lot of times you can get rid of that too, but that's cheating. Because that ring is probably 1/10,000ths undersized. And again, this is with the rough tool. Now if we come in with a diamond lap, so this diamond plate I'm going to run on the surface of the part here, and we'll see what we reveal. So this is a 45 micron, I think they call it a medium coarse. Right now we're riding on all the little high points of our shaft. You can start to hear how it's starting to settle in, breaking off all the high points. This is kind of like stoning in something, stoning in a ways on a mill or something like that. And you can see how I'm picking up some grit. Okay, so this is the coarser. I don't want to sit in one spot too long. Oh, and in fact, I should probably protect my ways. Let me lay a t-shirt over all of this. Okay, let me turn this guy back on, because you don't want diamond grit in your ways. That's sounding better, but that was the medium fine, so this is a kind of a coarser grit. I think this is 45 microns and the other was 25. Again, this is basically experimenting for the finished pass. I want to make sure there's no surprises when we get through dimension. I'm going to turn the spindle off before I get a rag in here, because rags can wrap up and pull your hand in. Yeah, after diamond lapping, it looks a little rougher, but the diamond brings out the true nature of your finish. So what we'll wind up doing is continue to lap down the finished cut, and what we want to avoid is the record player grooves, because as you turn a shaft, you get all these concentric grooves, which is a function of the feeds and speeds of your cutting tool. But we're going to actually be pistoning this shaft in and out of a seal. Okay, so it's time to do our finished cut. We are going to stick with the 576 RPM. We'll set up our coolant because we don't want to get heat growth on the shaft. All right, I did a light sanding on this shaft and did some measurements and concluded that we've got 1.5006 inches up here at the beginning of our area of interest, which is that green line, because everything out from this point over is going to be CNC turned down. And then in the middle of our shaft we have 1.5010, and there's clearly a few ring defects that need to be worked out. This line is the point where we're at 1.5000, or so right on the target here. Actually, there's a couple of shallow grooves on this side too. All right, let me run a smoothing Brillo across it. You can hide defects with Brillo pads a lot of times, but you can still see some of the remnants of our issues. I'm kind of holding the Brillo at an angle so it walks itself across the shaft. Doesn't hurt to try to get as much of the ring out, or the record player rings. Okay, I've roughed in the cylindrical shape using the diamond hone, and now I've got the 1 micron dial indicator hooked up onto the cross slide of the lathe with this little GoPro looking at it. So 1 micron is each little tick, and just for scale, 1/2 of a whole revolution would be a human hair. 1/1000th of an inch is from 0 to 25. So we can move back to the beginning where the chuck is, and we're going to do essentially a measurement. So I'm going to spin the part, and close to the chuck, naturally the diameter would be pretty well concentric, so you can see we're like 1/10 or so out of round. And then as we move the indicator down the part without spinning it, so we can get basically a cylindrical runout measurement. Keith's spec was within 1/1000th of an inch, and here, well, we're back at 0, but you can tell how we moved about 10 microns plus and 10 microns minus. So there we're back at it. There is a little bit of a flexure in this measurement because it's such a precise indicator. Just dragging the tip along the cylinder is enough to throw off the measurements a little bit. So, but you know, what are we going to do? So here we go again. Let's go one end to the other, and this is one particular facet of the cylinder. But the true test is to spin the cylinder and then keep doing this to map out a true cylinder in measurement coordinates. So we're going to move basically 25% or 90 degrees, and we'll drag across again. All right, it's time to do the CNC operations on the 2 ends of the piston rod. The first end of the rod is going to be the taper that is going to have the clevis pin hammered through. So it's the end that has the 3/4 inch to 12 taper on it, and an oval shaped 3/8 inch hole that Keith is going to hammer in his wedge pin in. So to do that, I've imported a DXF profile after I remodeled the shaft from the original drawing in 1932. So I've already written a program based on that DXF profile, and you can follow the tool step by step by turning the hand wheels. So you can see here this purple dot is depicting the location of the tool. And this tool location is the tool change location. So part of the CNC program is you got to tell the lathe where's a safe spot to start and where can I back the tool out to without crashing into anything, so I can change out tools and safely start the program. So that's what this pink dot is right here. And then what we're going to do is execute the program through a tracking function. So as I turn the knobs on the X or Z for the lathe, the lathe is going to actually play through in real time, and you can see on the GoPro that we are currently cutting air because I'm proving out this program. But right now we're gonna bulk out the material on the taper. That's why this tool is essentially just cutting back and forth. we're hogging out material, and the tool will give us a preview, or the preview window will show us the next window, or the next path that we're going to follow. So this is showing how we're basically just facing down the 3D profile. And then the final operation, or the next to final operation, is the first finish pass. And now the tool is actually going to follow the true path after we've hogged out all the bulk behind it to rough out the finish. And then the final finish, which I've set at 15 thousandths depth of cut, will come back and then it will execute the final finish cut. And you can see this dot is following along its path. Now I did set the 0 of the position not at the center of the stock, but out at the point of the corner of the finish diameter. And I just did that so we wouldn't have to look at a bunch of graphics. And it's easier to offset your cut, do the CNC cycle, and then measure your diameter, and then just do a tool offset to get the actual finish dimension that we're looking for, which is the tactic that we're going to follow today. Anyway, so that's the tracking, and you can also you can go forward or back anywhere in this program, which is kind of nice. So if you're not sure about something, you can just turn the knobs the other direction, and the program will execute all the way back to the beginning if you want. So that's kind of cool. All right, so let's exit out of the tracking preview mode, and then we will actually execute this program. Now I can also cut metal in tracking mode as well. So if you're not sure about your feeds or speeds, then as soon as you stop turning the knob, the cut will stop. So you can either exit the cut or adjust. Okay, so let me set up to actually run the program. So what I'm going to do is I'm going to move the 0 in 193 thousandths. And that is going to give us theoretically 10 thousandths of material remaining on our cut, so that we can then go back in or I can do a measurement and then do a tool offset and then replay the program to pick up the actual true dimension that we want. I will tell it X absolute because again we set the program up so we're not actually using the absolute center of the part for this. We can set the 0 anywhere in a CNC operation. Okay, so I think we are set, ready to begin. Press go. We're not going to do the tracking because I already did that operation. The stage moved to the tool load position. So we already have tool number 1 loaded. So I will turn on the spindle. It wants you to turn the spindle on before you start the program. And then we'll say feed go, which will start the program. And I'm going to be ready to stop it if I don't like what I'm seeing. And our first pass is skimming along. The way I programmed the program is I told it to start removing stock at the surface. So I could have saved a little bit of time by telling it that the stock was smaller than 1.5 thousandths or 1.5 inches. But you know, I also like to have a nice safety margin. This is a good way to check that you're not way off on your CNC program and it won't crash into anything. Oh, we can also show path, so let's do that. So the actual edge of our stock is skimming along where this tool is cutting right now. So after it goes out to the first rough pass, it will back off the part a little bit, depicted by this little red dotted line, so that it doesn't back scratch, and then go in and do the next cut. I always like to be ready to stop with a new program. So there it went back. And now we're going to enter our first cut, which is still a little light. I can override the speeds and feeds here. Oh, I think this is off screen. Let me zoom out so you can see what else I'm doing. Yeah, that's nice. Okay. So I'm going to go ahead and increase the feed just because it's a real light pass. And you can see the feed rate here is 2.9. I don't like to rush things. And our spindle speed is 550. And we can show different screens here. This is the program line that we're executing. We're not going to get into this detail. Show absolute, show incremental. Okay, so I'm going to reduce the feed now. We can go back to show path. because now we're getting into the cut. Let me make sure the GoPro is happy. Yep, that was good. All right, so there we go. So after this program completes, we will measure the end diameter and then do a tool offset to dial in the exact dimension we want. And then I can replay this program. A lot of times it's easier just to replay the program instead of trying to adjust it to speed it up. There we go, just cutting away, nice and easy. Got a little steam going on it. So you can kind of see the roughing tapers that it's machining into the end of the barrel there. There we go. So that's the tapers that it's roughing in. I believe it's 30 thousandths per pass. And basically the program is just hogging out these stair steps. Oh, now we're doing the first finish pass. So it's hacking off all the stair steps at this point. So you hear the chip load down and then ease up as you're going up the tiers of the rough cut that just went through. It does two passes because the loading on the tool bit changes as it's cutting off these stair step tiers. So it cleans up the flex and stuff that happened from the first finish pass with a second finish pass. So this, I believe, is its final finish pass. But we're going to do another cut after this to dial in the exact diameter that we want. I can also start playing with the feed rate to help dial in a good surface finish. Okay, and that's it. That's the end of the program. So I will wipe it off and we'll see what we got and measure the tip diameter. Okay, I'll get some calipers and then we'll check it out. I guess we can just do this real time. Whoop. I'm measuring the end of a taper, the end of a tapered shaft, so it's a little tricky to do. The micrometers are maybe not appropriate because the micrometer has a big, kind of a 0.2 inch flat measurement area. So having these skinny caliper jaws is a little better. There's 1.3075, so 1.308 is the, oh, in fact it just moved to 1.308. All right, so I'll figure out the offset and then we will update. All right, after checking that measurement a couple times, it looks as if we are 11 thousandths oversized instead of 10 thousandths. So the question is, how much do I allow for finish? Or maybe we'll do 10.5 thousandths offset. So I'm gonna bring the X down to 0 and then minus, let's see, we'll do the fine, minus 10.5. I'm gonna split the difference there. I'm gonna get it on. Okay, so X minus 10.5, so we're gonna bring the diameter of our taper to our finish size plus 0.5 thousandths for any sanding or filing or any finishing we have to do. And you know, again, measuring the diameter of a end of a taper onto a flat cylinder wall is a little tricky, so I'm adding some fudge factor into this. Okay, so let's say X and absolute set minus 10 point, well, just change it to 10.6, but that's okay. Okay, let's run this program again. Hi folks. Well, this piston rod's taking a little more time than I anticipated, and there's a little more fussy detail than I thought there'd be. So I'm going to go ahead and split the video up into two segments. So this week I will conclude where we are, and then we will follow up next week with the conclusion to the piston rod fabrication. Then I'll show how it all fits together, and we'll ship it off to Keith. Okay, well, enjoy your weekend. Thanks.